Hello and welcome to the tutorial in GeoStudio about the rapid drawing down condition. In this tutorial, we are going to study two cases. In the first case, we study the slope solidity of this dam during a gradual process when the water reduces from the normal level to the bottom of the reservoir. In the second case, we are going to study the factor of safety for this dam, but with the instantaneous reduction from the normal water level to the bottom of the reservoir. Let's go. So in the first step, we need to create a new analysis, and the pattern analysis I choose here will be Shift W because I'm going to study the rapid drawing conditions. And the first one, I change this one to initial condition, and I didn't change any default one. Later, I need to simulate the rapid drawing condition, so I need a transient analysis. So I add a sub one will be a transient analysis. And this is the first case, so I press this one. And it is the first analysis in the first case, so 1A, draw down with time. And in the time, I change the duration to 30 days with 10 steps and exponentially at 0.5. It will help me to have beautiful daytime. And that is, after that, for this one, I need to add a slope analysis for limit equilibrium. And please remember that you need to import the pore water pressure from on, not last. And as I told you before, Morgenstern price is my favorite one, and I do it from right to left because it slides into the reservoir. Okay, no tension crack, nothing. You can choose linear search or root finder. It depends on the method you use. Now, I need to change this one to 1B to be distinguished from the other conditions. And now I go back to initial condition and add a new subcase that I'm going to use Shift W and transient. And for the time, same thing, I use for 30 days with 10 steps, and exponentially increment is 0.5 day. And to be distinguished from the previous one, I do it 1 to A, instant withdraw, instant drawing down. Now, and I need to compare the effect, so I also need to add a slope analysis for limit equilibrium from all of the above. And as told you, Morgenstern price is my favorite. Just click on right to left, so it will slide into the reservoir. And I think that is for this part. Now let's start drawing geometry. When you draw the geometry, you can draw in the root analysis or you can do in the 2D geometry component. It's all up to you. I often draw in the initial condition because it has more comment on the top for me. So now let's start do the geometry of the dam and the foundation. I will draw a very simple one because we focus on the effect of rapid drawing, not the geometry. So my dam has a foundation depth of 10 meter and the length should be about 100. Yep. And on the top, I will draw a dam, maybe right here, with a height of 10 meter. So it should go up to 20, and it must be wide. So I put this one is about 1 to 3. If you want to do it with accuracy, you should add point first, and after that you can try to add the polygon between the points. The last thing I need to do is my drainage. Yep. So here is my geometry. Okay, so in the next step, we need to define the material properties. And I click on define and material to define them. And click on add to start defining the material. The first one I want to do is the foundation, which should be sandy silt. And because it's all the way under the groundwater level, so therefore I choose saturated only. And my saturated conductivity will be 0.1 meter per day. Yeah. And the volume water content should be 0.5. Compressibility default to -4. I just made up the number because we focus on the effect, not on the material or the geometry. This is a very simple tutorial only. And for the dam, I make this one should be silty sand. And because half of it is above the groundwater level, so I must choose saturated, unsaturated material, and I need to define the functions for the conductivity. In the first step, you define the water content function. So click on this one and add a new one. So it should be water content. And you choose the data point function to use the standard estimation. My water content is 0.5 and it should be sandy silt. I don't have it here, so I choose silt. And my magic function is 200. Okay. And my compressibility is 2e minus 4. If you click on the edit data point, you can see the estimation for your function, and you can change the data point by clicking on the value of the data and change it. But the standard estimation is fine for me, so I just close this. And from the drop list, I choose the water content, the function I just created. In the next step, I need to define the conductivity function. So I click on ellipsis and add a new one. So it could be conductivity. And in the type, I use a k with data point functions and use a standard estimation. My water content function is water content that I defined before. And my saturated kx should be 8.64 meter per day. And residual water content, I would use this as 0.05. And the suction is the same as I used before, 200. And okay, so here is my estimations. If you click on edit data point, you can see the estimation for this one. I think it's good to me. I just close this and choose a function from the one I just have. And I have isotropic material, so ky over kx, I choose it as 1. And that is enough for me. Now I need to identify the material property for slope. So I click on any of the slope analysis and click on define and click on material. Now I need to identify, so I choose a simple one, that's a more column, which the unit weight for silty sand will be 19. Cohesion should be 2 and 5e30, for example. And for sandy silt, I use unit weight is 17, for example. Cohesion is 20 and phi is 28. and that's good for me. Yep. Now, in the next step, I need to apply the material to the analysis. So I just click on draw material or assign material, and I click on apply to multiple analysis and click on all of them. For the sandy silt, it should be the bottom one, so I click on the bottom. And this one as well. Yep, and for the silty sand, I click on the top one, and that's it. So when you click on all of the other analysis, you will see that the material will be assigned to all of the analysis. After assigning material, you need to define the boundary condition. So for the water condition, you need an additional point over here. So I use draw point and zoom in to get something as 19. So should be this point. So this will be the input point for the water level in the reservoir. Now I need to define the hydraulic boundary condition first. So I click on define and boundary condition. I just delete all of them because I don't need them, and add my own. So I create a new hydraulic boundary condition. The first one should be the upstream and should be the total head at 19 meter. So I will keep it at red. And after that, I add the one for the downstream. And it should be the water total head at the level of 10 meter. So therefore, it should be constant at 10 meter. I change this one to something I can know, for example, green. Now I need to identify the boundary condition for the rapid drawing. So I add up a new one, and it should be draw down. And I choose water total head, but it's a function of time. So I click on this ellipsis to define my function. I add a new function first. And I name this function will be level with time. And I choose a type will be supply data point function. And here I can add up my new data point. So for the first example, in the day 0, I have the water level is 90 meter. And for day 5, I have the water level is 10 meter. That is the bottom of the reservoir. And here is my functions. I think that's good for me. So I just use this one and choose this one from level with time. Now, the last one I need to do is a seepage phase when it has no water on this. So now I need to add a new hydraulic condition. And I choose this one to be the water rate. And it would be constant at 0 cubic meter per second. And I also need to double check the potential seepage phase review for this rapid drawing conditions. And that is. To avoid some confusions, I think I may change the drawdown color to something like orange or yellow. So the color will be very different. Now, after defining the boundary condition, we need to assign them to the line we need. So for the initial conditions, I have nothing changed. So I'm going to click on draw boundary condition. And for the upstream, I click on this line and this line. For the downstream, I click on this line because it's a drainage. And that's it. Now for the draw with time, I'm going to assign the drawdown to this line and the downstream side to the same location. For the install drawing down, I apply the upstream, the downstream to the downstream side and to the bottom of the upstream side, and I apply the seepage phase to the slope of the dam, and that's it. If you want to double check which one you have assigned, you can click on Define Boundary Condition and click on Assign. Now you can see the list of the line has been assigned the boundary condition, and you can double check if it's right or wrong for you. In here, I think I just change this one to seepage phase to avoid any confusion. And that is. In the last step, we need to define the potential curve of failure. So we need to go to the slope analysis and try to draw the entry and exit. So because we start from right to left, so therefore we draw the exit first. I can draw to up to half of the slope. And for the entry, I draw from the other side down to half of the slope. Yep. So that is. And I do the same thing to the other. I should rename this one to 2B to avoid any confusion later. And now I draw the exit and entry. And next one I draw from the other side down to the middle point. Okay, and all good. I think I'm ready to start now. And before we start, we need to save it. So I save it at a test file and save it. It will take a while because we have several analyses. So here are our results, and if you click on the 2B, the instant drawing down within 30 days, you will see that the factor of safety is 2.056, and if you click on the slope stability for the gradual reduce, you will see it's 2.061. So the numbers are very close and acceptable. However, if you click on the process, you will see it's different. So if you click on this one, you will see that it starts from 2.3 something and it's reduced to 1.8, 1.7, 1.6, 1.8 again. So it's about 1.6. If you click on the instant drawing down, you will see that it starts from 2.3 as before, but it goes down very quickly to 1.2, 1.4, 1.5, 1.6, and go up again. To have an overview on the slope stability during two different processes, you can draw a graph by clicking on this button. And now we add a new graph. So for the things for the kind of graph, we click on sleep surface and don't choose the current but choose the critical. So always go for smallest one, and sleep surface factor of safety against time. So you can see here for the 1B, it starts from 2.3, go down to something about 1.6 something and go up again. However, if you click on 2B, you will see that it starts from 2.3 something the same, but go rapidly down to 1.2 and then go up again before it stabilizes around 2 point something. So you can see that a very different effect of the drawing process to the stability of the slope. I think that is for today. I hope you enjoy the tutorial and see you in the next video. Thank you.